Uh, I want to talk today more. Today is this whole week is about power series, and specifically, there were some lemmas that we stated that are used to estimate. I mean, our main theorems that we use are the Weierstrass M-test, etc. But to be a bit able to apply that, we need some lemmas, and this is mostly a review of 131a. So, and then we'll at least get to state our theorem and define radius of convergence, and hopefully outline most of its proof. If we get to state something about uniqueness, that's great, but most likely this will be go to Friday. Also for this topic, tau doesn't include very much, so I will be writing notes, LaTeX notes for that, so you know what is really being tested. Okay, so let's keep our goal in the mind. We're talking about convergence of power series, so a n x to the n, or I mean, you could have x minus x0 to the n, but usually we do the change of variables, y is equal to x minus x0. And how we estimate these, you can think of the example that we did on Monday, is that we want to estimate the coefficient here by a power, b to the n, because then this whole thing becomes bx to the n, and you can understand it by a geometric series. This is similar to like in your homework that you have 2 minus n 2 minus n x to the n. Okay, there's some that sign nonsense, but what you can look at this is really x over 2 to the n, and therefore any estimate on x is already very useful. So geometric series will play a role, and to get this estimate, we'll need to talk about lim sup, because that's the most general thing. Now, because we want to talk about derivatives, and when you differentiate this power series, what happens is that you get these powers of n there. You get n minus 1 if you take the second derivative, n minus 2 if you do higher order derivatives. So if we are committed that everything we will do is estimate by powers, then we also have to estimate polynomial things by powers. Okay, there's a little bit of a choices that are delicate, but into making this work, but it's good to keep in mind that why we're doing these things, and maybe that helps organize this slightly difficult topic. So we stated last time this lemma, that if you have n to the d, you can always bound it grows slower, or you can bound it from above by any geometrically growing thing, b to the n, by some constant that depends on the degree and the base b. Okay, let's look at the proof of this. This is an induction proof, but there's a slick trick here that's a little difficult to get. So the idea here is that, okay, how fast is this growing? When you go from n to n plus 1, you're multiplying the whole thing. So n plus 1 to the d is equal to n plus 1 over n to the d times n to the d. And the idea here is that, okay, this is a certain multiple of that, and this multiple here will eventually be less than b. So then the next term is at most b times that term, and that is why it's growing slower, because it's a smaller multiplicative factor. So let's make that rigorous. So, okay, if we fix d and b as above, then we first have to choose CBD. So we use the fact that the ratio of the two consecutive terms is going to 1. The power is continuous, and the argument is converging to 1. So there exists a capital N such that n plus 1 to the over n to the d is always less than or equal to b, because b is strictly bigger than 1 for all n bigger than n. So now what we do, this allows us to, we fix such an n, and then we let CBD to be n to the d for such n. The idea is that this may grow faster than the geometric thing, but only up to this nth index. And after that, we will use this fact. So somehow this constant absorbs the first capital N terms here. So to prove that rigorously is by induction. And it looks a little different, funny, because there's actually, it's nice to look first at not the case just n equals 0, but actually simultaneously all cases from 0 to n. So let's see what we have here. So if you are in this case, then n to the d will be less than or equal to capital N to the d, will be less than or, well, this is equal by our choice, c, b, d. And because b is bigger than 1, this is less than c, b, d, b to the n. We're done with the first part. Okay, so this is what I mean by this absorbs kind of the first terms. It makes, if you want to get it bound for finitely many things, essentially the maximum of those terms works. Okay, what about going from n to n plus 1? Well, if n plus 1 is less than or equal to n, capital N, we're automatically true, because we just said that the case was true for all indices less than n. So the conclusion of this implication is true, so there's nothing to check. So we only have to check if n plus 1 is actually strictly bigger than n, capital N. But if this is the case, then n is bigger than or equal to capital N. So then what we can use is we can write n plus 1 to the d is equal to n plus 1 over n to the d times n to the d. The first constant here is less than b by induction assumption, by choice of capital N, because we are bigger than capital N. And the second term, by induction hypothesis, is less, well, let's keep this actually separate. So first, the first term is less than b n to the d. And then by induction hypothesis, because n, the claim is true for n to the d, n is less. So we get b times cbd times b to the n. Now you merge the powers, you get c, bd, b to the n plus 1. And this is exactly the claim for n plus 1. Okay, so to make this a rigorous proof, all we would have to do is then by induction principle, the estimate is true for all n. Any questions? Okay. So this is a rigorous proof that polynomials always grow slower than geometric things. I mean, this is very intuitive, but this is one proof for it. There are others. There are other ways of seeing it.